Thank you, and thank you for having me. So, as Yoshua said, I'm going to talk to you about sort of some of the research work that the Google Brain team has been doing, and with a bit of emphasis on the software tools that we've put together to kind of enable that research. And I'd like to point out this is work represented of many, many people here. This is not only my work. There's literally hundreds of people at Google who have been involved in various pieces of the work that I'll show. So by a bit of background, the Brain project actually started about 5 years ago. And we had this hypothesis that the time was sort of ripe for neural nets, particularly if we could apply large amounts of computation and train very large, powerful models on large data sets that were starting to be available. And just kind of understand what was possible initially, mostly in the field of perception, and gradually we've migrated to language understanding and other kinds of tasks, as you'll see. But initially we were focused on speech and vision tasks. And I'm going to cover kind of some of our experience from the last 5 years, both on the research side in terms of the research work we've done in various different kinds of areas, both sort of pure machine learning research and also research in various domains like speech and images and robotics. And then also I'll talk about some of the production aspects of actually getting this kind of work deployed on real Google products, because deploying these kinds of models, which are computationally intensive at scale, where you have many tens of thousands of search requests per second, and you need to run many neural net inferences for every one of those, that's somewhat challenging and offers different kinds of systems challenges than training neural nets. The focus of the talk will be mostly on what we've been doing in the area of neural nets, but a lot of the software that we've built is actually more general. You can use it for all kinds of other machine learning algorithms. You can actually use it, TensorFlow, for sort of general purpose numerical computations. We've seen some interest outside of Google in using it for what you might traditionally think of as high performance computing applications. So one interesting thing about the Brain team is we kind of bring together people with a mix of computer systems and machine learning research expertise, and kind of put them to work on interesting machine learning research problems and building software and distributed systems and hardware systems that really make sense in the context of accelerating that kind of research. So we have this kind of nice blend of different kinds of expertise that collectively we can do things that none of us could do individually because we don't have one person with all these different skills. And so we do pure machine learning research, and we also do research in the context of emerging machine learning application areas, particularly things like robotics and language understanding. We're starting to do some work in the field of healthcare as well. So we disseminate this work in lots of different ways. We publish a fair number of papers. Recently, we've released TensorFlow as the core machine learning system that we've been using internally as an open source project that I'll talk about. As part of that, we're starting to open source models associated with research papers that we publish so that people can reproduce our work and build on it more readily than just reading an English description of some paper. And then we collaborate with product teams at Google to get our research into real products. OK, so what do we actually want in terms of machine learning research? We want to be able to build really intelligent systems that can learn from experience. And that experience can be sort of static data sets that exist on large storage systems, and we just want to learn from the data that are there. It can mean agents operating in some simulated or real environment and collecting experience as they go. And then we want to use those intelligent systems to actually solve problems that people have in the world. And so I'll touch on some of those. And so what do I mean by understanding? Well, if you think about what humans are able to do looking at raw forms of data like this, if you look at this image, none of you would have any problem sort of telling me a descriptive sentence about what that image represents. Similarly, you don't have any trouble finding all the text in this image, because assuming you can read, and identifying what kinds of stores those are from the context. But computers traditionally have been pretty bad at this. And you don't have trouble understanding what I'm saying, hopefully, But computers have traditionally not been that great at that. They have much higher word error rates than people listening to other people speaking. And particularly with more mobile devices, having really good speech recognition is actually quite important for building the kinds of experiences we want to build in terms of how those devices get used, because typing is a pain. Getting back to one of Google's initial products, search, traditional information retrieval techniques basically take the words in the query, and then they kind of look roughly for matching words in documents and consider things like proximity of where those words occur and so on. But really, as a human, you have a much higher level of understanding of the language of documents and queries, and you know from reading these two snippets of documents that the second document is a much closer match for what the user probably wants than the first one, even though the first one has all these highlighted red terms that seem to match the terms in the query. So knowing at a high level that this is a good match for that document, that the second document is a much better match for the query is another thing we really want to get out of language understanding systems. So here's just some example needs of the future that we would like to be able to solve. The first few we can basically solve today, the first two. And then they get kind of progressively harder, I think. But these are sort of the high level. This was taken from a talk I gave at a database conference where people were wondering what the future of database systems should look like. And I sort of was trying to motivate them to say, OK, you have all this data, but really what you want is to actually understand the data at a level that you can answer these kinds of queries, not that you can select this column and where the other value is bigger than 20 or something. So I think these are kind of the aspirational things that we need to work towards in solving. I particularly like robot fetch me a cup of tea from the snack kitchen. That'll require solving lots of interesting problems. So when the project started, there was basically not much use of deep learning at Google about 5 years ago. And our group started dabbling with on sort of unsupervised learning research, and also worked with the speech recognition team on speech recognition, and actually deployed the first production use of neural nets at Google in the context of our speech recognition system. And over time, we started working with a few more kind of computer vision problems, and other teams would hear about the success that some team had in solving some machine learning problem. And one of the really nice properties that deep learning has is it's very widely applicable to all kinds of different problems. And so you see the breadth of different kinds of areas that people have applied this to, and the growing use of this within Google. This is kind of the number of unique directories within our large shared source code repository that have configuration files for our two different machine learning systems checked in. And that graph continues to go up. So I will, as part of this talk, discuss TensorFlow and show a real example of how we've used TensorFlow for different purposes. And I'll also explain what's happening underneath the covers. So if you ever use TensorFlow yourselves, you can kind of have a better mental model of what the system is actually doing underneath covers. So we've actually built two separate systems in the course of doing our machine learning research. The first was a system called Disbelief that we built and published a paper about at NIPS 2012. And it had the properties that it was very scalable. So we ran some experiments as part of a different NIPS paper, ICML paper, on 16,000 CPU cores to train a single model. So it had the nice property that you could actually throw lots of data at this problem and have fairly computationally intensive models. But it wasn't super flexible for research. It was very good at actually being sort of production ready. So you could take a model you've trained and push it out into production. But it wasn't that flexible. Like if you wanted to do something other than a feed-forward neural net training, it was kind of annoying and hard to specify if it didn't fit the programming model. So our second system, sort of based on what we learned, actually keeps what we think are the good properties of the first system, which is that it's scalable and good for production use, but generalizes things and simplifies it a lot, actually, and makes it much more flexible for a variety of different kinds of research purposes. It also enhances the portability, so we can actually run TensorFlow models on lots of different kinds of devices, as you'll see And we open sourced it with a fairly freewheeling license, so you can kind of take it and do whatever you want with it. So one property of neural nets is that the results tend to get better if you're able to train on more data. But when you do that, you also often need to train that system on using a bigger, more powerful model, either more capacity in the model or more computational complexity somehow, in order to sort of by giving it more data but not increasing the size of the model, at some point you saturate the amount of information that model can learn. And you really need to do both things, scale the model up and scale the data up and then scale the model up so that you can pick up on the more subtle patterns that occur only rarely but are now common enough across a larger data set that you actually see them and the model can generalize from them. And the combination of those two things is actually quite painful from a computational perspective because it's almost like the product of these two factors that defines how much computation you need in order to actually get the model to train. This is taken from a paper published in 2015, but you can see similar kinds of trends in lots of different machine learning papers. This is comparing a language modeling task, looking at how the perplexity changes as you increase the size of the training set. So this first graph is billions of words. And you can see that the perplexity generally goes down for lots of different kinds of language models. This is a traditional n-gram model, and this is an RNN with 2,048 units. And you can see that having a larger data set actually helps you a fair amount. Similarly, if you hold the size of the data set fixed at 1 billion words, but increase the size of the model from 128 units here to 8,192 here, you actually get substantial decreases in perplexity as well. And if you do both those things, presumably it's going to be even better. They didn't actually do that experiment in this paper. So this combination works really, really well, but it poses pretty interesting systems problems. In particular, you need lots of computation in order to do this, and you also want to train and do experiments quickly. So the most efficient thing to do, if you didn't care about training time, would be to do these computations on, say, a single GPU card, because then you don't have any communication overhead or communication bottlenecks. But in order to actually get the system to train in reasonable amounts of time, you actually have to generally go beyond the barrier of what fits on a single device or a single machine and use lots and lots of machines to train models quickly. And a sort of related idea is the latency at which you can perform an experiment really influences the kind of research you can do. If your experiments take a matter of a few hours, that's a very different feeling than if they take a few weeks. So I'm going to skip this and just talk about some of the initial. The first thing that we worked on with our speech team was just replacing the acoustic model that they used in the speech recognition system with a fairly deep feed-forward neural net that tried to predict which phoneme was being uttered in the middle 10 milliseconds of this window. And that actually dramatically improved the word error rate in the speech recognition system. It actually required fairly intensive training, so we were using several hundred machines to train this model for several days. And
700 machines?
Several hundred. I think it was maybe 400 or 500, something like that. This was before we had GPUs in our data center. So one way you can compensate for not having GPUs deployed yet is use more CPUs. And over time, the speech team has sort of continued to evolve the kinds of models, and they've been getting more complicated. So this is a model that they published last year that has some convolution at the bottom and some LSTM layers at the top, and then some fully connected layers. LSTM layers in the middle and fully connected layers in the top. And not that this is exactly the end-all, be-all model, but it's an example of something where you want flexibility to try lots of different kinds of models and understand what works well, what doesn't. And the more recent trend has been to use sequence models of various kinds, recurrent LSTMs typically, with attention that can model the entire thing. So rather than separating the speech problem into an acoustic model where you try to predict parts of words, and then you have a language model that takes sequence of parts of words and stitches them together into the actual phrase that the user uttered, it's actually more efficient and allows you to optimize end to end to just train the whole thing jointly and allow you to have the model adapt to whatever makes sense and not necessarily have this artificial barrier of phonemes inserted in the middle of the speech pipeline. And so our group and the speech group have continued to push on this idea. Similarly, in the image recognition field, this was kind of a seminal paper that really showed that deep convolutional nets could be used for image recognition. And it's a somewhat complicated thing. It's got multiple parallel towers. Alex Krzyzewski actually sort of hand parallelized this computation across multiple GPUs to get more efficient computation. And then over time, some Google researchers actually developed a little module with a more complex pattern of convolutions of different sizes and sequences of convolutions. And then that basic module gets replicated a whole bunch of times in a fairly deep model. I think if this one's like 26 or 30 layers or something, but actually gets substantially better results. Where each one of these boxes is maybe 10,000 neurons, represents a fair amount of computation. And so that was published there. And you can see why people are excited about neural nets for image recognition. So before people tried them in ImageNet, the error rate was hovering around 26, 27% for the few years that they held the contest before then. And then Alex and Ilya and Jeffrey came along and really dramatically dropped that error rate. And the next year, my summer intern, Matt Zeeler, started a company and won the next year. And then there's been just a progression of improvements since then. I particularly like this result, which is Andrei Karpathy, who helped administer the ImageNet contest as a PhD student at Stanford, was really actually wondering what the human error rate on this task would be. And so he tried to convince all his lab mates to actually subject themselves to tests, but pretty much only he did a good serviceable job of it. So he did 100 hours of training on a training set of images, and then set those aside, and then subjected himself to the test set, and he got 5.1% error. And another lab mate of his that only did like 10 hours of training and then gave up got 12% error. ImageNet is actually pretty hard because it has like 40 kinds of dogs that you need to discern. So another interesting trend to notice is that the number of parameters in these models has actually been going down generally, or it went down and then it went up a little bit. And that's actually important for some kinds of applications because the number of parameters really affects the size of the model that you're going to deploy on say, a mobile phone. And so those actually are pretty nice from that respect. It also makes it harder to overfit in a lot of cases. But anyway, that's why computer vision is working so well, because the error rate's gone from 26 to 3%. OK, so what kinds of properties do you actually want in a machine learning system? So one is you want this ease of expression that I've been talking about, where you want to be able to take any kind of machine learning idea, combine it with a reinforcement learning system that might interact with an agent, and be able to express all kinds of exotic models in a way that's easy so that you can try them out without too much effort. And then you want the system to be scalable so that you can take that model you've expressed and try it on not just small data sets, but on sort of realistic data sets for real world tasks like speech and vision and language. Depending on your needs, if you're a researcher, you may not care much about portability. You may just want to get the answers to your experimental questions and then go on to the next experiment. But if you're going to deploy these things in production systems, often you do care about portability, where you want to be able to train the models on, say, a cluster of machines or on a desktop machine with a bunch of GPUs in it, but then maybe deploy the model on a mobile phone. And another thing you care about is reproducibility. So you want it to be easy to share results and to reproduce other people's results in a way that actually you have confidence that you've actually reproduced them correctly. So being able to share actual working implementations of the research that people have done is pretty important, rather than, because often you'll read a paper and it'll say, well, we initialized with a low learning rate. And you're like, well, I have no idea what that actually means in practice. And then for some kinds of applications, if you actually want to deploy this in real products, you want the system to be able to take that research idea and then express it in a way that can go into a real product without re-implementing it in a different kind of system. By the way, I'll take questions anytime people have them. And so TensorFlow is kind of the second system that we came up with. And I'm going to talk to you about some of the attributes it has. So I did say this was work of a lot of people. So this was the white paper we put out with the initial TensorFlow release. It kind of describes some of the inner work systems aspects of TensorFlow. It also describes the visualization system that it has a bit, and the programming model a bit. We actually have taken that and adapted that content with more of a systems focus, and there will be a paper that it's going to appear in this year's OSDI. We just found out last Friday that it was accepted, so that's good. That's more about the systems aspects of the machine learning system. And we've seen pretty good adoption of TensorFlow. So we had about 50,000 binary installs in 72 hours right after we released it, and about 500,000 since November. And it's unclear if GitHub stars and forks are a great measure of engagement, but it is one measure, and by those metrics, we're doing reasonably well. One stat I do like is that we were the most forked new repository in GitHub in 2015, despite only being available in November. So I guess that's good. And it's sufficient that Bloomberg has taken notice of deep learning open source packages. And they published an article a week and a half ago discussing how many stars different open source packages have. So the blue line is TensorFlow, and there's a bunch of other ones represented there. I don't know what it means that Bloomberg is writing about deep learning packages, but it seems interesting. So one of the things that I think went reasonably well with the release was that we put together some tutorials that describe how to use TensorFlow to implement various kinds of interesting machine learning models. And people really like those tutorials because they talk both about kind of what is happening from the mathematical machine learning perspective, but also what's happening in the expression of that algorithm or system in TensorFlow. And so we have things like a convolutional neural net model for images, a vector, like a word-to-vec implementation, a simple RNN, a sequence-to-sequence model for translation. And people can kind of work through those and understand what's going on at a reasonable level. So as I said, the motivation for TensorFlow was really that it wasn't as flexible as our first system wasn't as flexible as we wanted. And based on that experience, we actually could simplify a lot of things that I'll show you in a minute, particularly around how parameters are managed in the machine learning system, and also make it more flexible. So the core bits of TensorFlow are basically this graph execution engine. So the computational graph, the model of computation is you express a computational graph, and then this graph execution engine is responsible for executing that. And it's responsible for dealing with different kinds of devices. It has different implementations for different kinds of operating systems and platforms. And then there's different front ends for specifying and driving this computation. So the most fully developed ones today are Python and C++. Most people use the Python front end because it's sort of the most fully developed. That's what all of our researchers use. We've actually gotten some pull requests from external contributors to add other language support. So there's one to add Java, I think, and there's one to add Go support, ironically, from Facebook, which is kind of maybe we should have gotten to that first, but we didn't. So the basic computation model is a data flow graph where the nodes are different kinds of operations on tensors, and the things that flow along edges in this system are tensors, not in the like actual mathematical tensor sense, but in the n-dimensional array kind of caveman's interpretation of a tensor. And the tensors have types, so you can have like a 3-dimensional tensor of floats or a 2-dimensional matrix of ints. And then you essentially build your graph. So for example, you can read a data set, and then you can create some placeholders, which I'll talk about in a minute, and some variables that are going to hold the parameters. And then you can say, I'd like to do a matrix multiply of these two things and add a bias term and do a softmax. And that's going to be the output of my model. And unlike pure data flow graphs, we've actually augmented the data flow graphs in TensorFlow with a notion of variables and operations that update variables. So that's basically how you have state in the system for holding parameters. And so, for example, here we have biases, which is a tensor, and it flows into this computational graph. And eventually, we compute some update we want to make to the bias variable, and we do a minus equals operation on it, and that allows us to update the state there. Taking a page from Theano, one thing that people really like about Theano is the symbolic differentiation support. So you don't have to write your own derivatives. The system just has derivation, symbolic differentiation built in. And so you can say, I'd like to minimize my model with respect to this cross-entropy loss, and it sort of does the right computation. And I'll show you later on what that actually reflects to in the computational graph. And then typically, the way that people use this is they launch the graph and run the graph multiple times, once for each mini batch in a deep learning application. And so here you might say, OK, I'm going to get from my training data, I'm going to get the inputs and the outputs. And then I'm going to run a training step where I'm going to feed in the batch of examples I read and feed in the labels that correspond to the elements in that batch. And then the system will go ahead and run that computation. So this abstract model of a graph actually can't directly be executed because we need to actually place where different pieces of this computation are going to be performed if we have multiple devices in our system. And so a very simple setup is you often have a CPU and a GPU card in your machine. And you want to be able to execute this graph. And perhaps some of the operations maybe don't have GPU implementations. So maybe in an image model, for example, there might be an operation that decodes a JPEG encoded image into the unpacked 3-dimensional red, green, blue height and width tensor of the actual image data. And maybe that doesn't have a GPU implementation, and it only runs on CPUs. So the system is responsible for understanding where different operations can be placed and to try to place them in a way that is most efficient for executing the graph as quickly as possible. And so it might decide to place things here. And when it does that, the system transparently inserts these things called send and receive nodes that are responsible for managing all the communication across device boundaries. And essentially, it's a pull model. So you start executing a receive node, and the receive node kind of implicitly knows which send node on this other device to contact, and says, please give me the biases variable I'm waiting for. And if it's available already, great. If not, then that receive operation will kind of hang out until that data is available and then transfer it in whatever way is appropriate for the two different device pair that's involved. And so there's kind of the rewritten graph that you never see as a user, but actually kind of is what it looks like under the covers. And one really nice property about this is that by having just send and receive nodes be responsible for transferring data across device boundaries, you encapsulate all the communication of the system into just the send and receive node implementations. And you can have different implementations for the different kinds of devices involved. So for example, if you have 2 GPU cards on the same machine, you can actually do a GPU to GPU memory copy without involving the CPU other than to start the copy. And if you have CPUs on different machines, you can do a cross-machine remote procedure call. And if you have GPUs on different machines and your network supports it, you can do RDMA, sort of remote direct memory access, that allows one GPU on one machine to reach into the memory of a GPU card on another machine and pull out, this particular tensor directly without involving the host CPU or having to go through the host memory card. Yeah, is that a question? So we don't have an MPI implementation, but essentially if you wanted to have MPI support, you would add an MPI implementation of the send and receive nodes. And that's relatively easy to do. You can have different implementations of these nodes. We do, for example, within Google, there's one RPC subsystem that we use that has some extra monitoring. And then a variant of that is what's open sourced as the gRPC open source subsystem, but they're slightly different. So we have 2 implementations of the RPC subsystem that we can swap in and out. We've been sort of continuously working on improving the TensorFlow system, as have a bunch of external contributors. So in November, that was the initial release. And in December, one of the things that we heard was that people really wanted Python 3.3 support. There were a bunch of improvements made to GPU performance. Our performance out of the gate was actually a little sad. We'd been measuring it with our own GPU compiler toolchain inside Google. So we weren't using NVCC, we were using gCUDA-CC, which is a variant we've built internally for compiling CUDA code. And it turned out our internal compiler dealt much better with 64-bit tensor indices. And so the NVCC compiler actually was 20 or 30% slower for every time you indexed into a tensor, which in TensorFlow you do fairly often. So we fixed that by moving to 32-bit indices in a lot of cases to fix some of the performance issues. In February we did another release, and one of the things that I think is important to understand about TensorFlow is the lowest level representation of the graph has very sort of low-level, fine-grained operations. And that's great for researchers who want to control exactly what kinds of operations are being performed. But for some people, they want a much higher level abstract view of a neural net. They want to say, I want 5 layers of this width, and they want that to be concise and easy to express. And they don't necessarily want very fine control over every last aspect of how those things work. And so we think what will likely happen is there'll be a whole bunch of different higher level APIs that people use to specify TensorFlow graphs. And you can also use kind of the native raw TensorFlow operations graphs. And so we have one that we added that has sort of some higher level support. There's also Keras, which is a popular open source package that has been ported to also be able to use TensorFlow as a backend. Some people like that as a way of specifying models. So I think it's not like we will necessarily standardize on one way of specifying computations, but what we hope is that many of those map down onto TensorFlow graphs, and the optimizations we're doing and will improve on will benefit all those higher level ways of specifying these different systems. So our April release added a distributed runtime. So our initial open source release didn't have a distributed runtime, and that was one of the things that people really wanted. And the reason it didn't have it was we just hadn't yet implemented the gRPC transport subsystem for send and receive nodes. And so we implemented that and got that to work with Kubernetes containers as the basis for running many different processes in a distributed system and communicating between them. And then more recent release, we've added iOS support and GPU support on macOS and FP16 support, which is going to be important with upcoming Pascal cards from NVIDIA, for example. So anyway, the main point of that is just that there's been pretty steady improvement in the kinds of things the system can do. And this is a graph of activity to the GitHub repository. So since November, we've had about 6,000 commits of various changes, which I think is like 20 or 30 a day or something like that. And actually, the majority of contributors are now outside Google, although the heaviest contributors are within Google. So our colleagues at DeepMind were mostly doing a lot of their research in Torch, but they've decided to move to TensorFlow to standardize sort of within Google what we use for sort of our deep learning research and also production and deployment of deep learning systems. As one of the things that we do is also release pre-trained models in TensorFlow, where we release not just the model description, but also the parameters. So this is the state-of-the-art inception model that we released, the pre-trained parameters, so people can use that in various ways to do different things. And there's a tutorial that shows people how to take that model and run it on their platform. There's also another tutorial that shows people how to use those pre-trained that pre-trained model to then use it as pre-training for a different image classification task where you might have a small amount of image data on your own. And that's Grace Hopper, although we identify it as military uniform. OK, so one of the main motivations for doing all this computer systems work for machine learning is really to make experimental turnaround time much lower than it would be if we're using sort of non-distributed approaches. And it's really just a very fundamentally different feeling doing research when the experiments take, you can do multiple experiments per day, let's say, than if it's something where you have to launch it and then wait several days or even several weeks. And then you get your results, and then you're like, oh, well, why was I running this in the first place? I kind of have forgotten at this point. And so that really is a big focus of us, is to make that turnaround time as low as we can. And one of the ways we do that is with large amounts of raw computing hardware, but you also need to make it easy for people to use those computers. You can't just sort of throw raw computing hardware and expect every machine learning researcher to also be a distributed systems expert and know how to use, say, for a rack of GPUs in raw form. And so TensorFlow is this system that is fairly abstract in how you specify the model, but then the system will map that down to a bunch of hardware that you say, OK, I have the ability to use 32 GPU cards for this experiment. So one of the ways you can get faster training is through data parallelism. And the idea here is that you want to use multiple model replicas that all kind of collaborate to update the shared set of parameters in the model. But they're all going to be training on different data. The speed ups that you can get here depend pretty highly on what kind of model. So for dense models, we regularly see kind of 30 or 40x speed up using 50 replicas. So it's not quite linear speed up, but it's quite good, because it means with 50 replicas, you move the time from a month down to a day for an experiment. And that's pretty compelling. For sparse models, where you have like a bunch of embeddings for vocabulary items, and a given example only touches maybe a handful out of millions of embeddings, you can support many more replicas often in those kinds of environments. So we regularly train models with 1,000 replicas for some kinds of applications that have these very large sparse embeddings.
So
Yeah.
why is it the scaling is better in that case?
It's just you get less interference with the gradients from the multiple replicas. So if you're only touching 5 words in a vocabulary, the odds that another mini batch on some other machine has touched those same words is pretty low. So you still have interference for the shared part of the model, but that tends to be updated. The change in those shared parameters tends to be slower. And so you end up just being able to support more replicas before you kind of fall off a cliff. OK, so the way this works, this is kind of a diagram from our earlier system, disbelief, is we had this set of machines called parameter servers that are going to be responsible for maintaining the current set of parameters in the model. And then we're going to have a bunch of model replicas, which themselves might be multiple machines or multiple devices. And before a given model replica actually processes a mini batch, it's going to download the current set of parameters from the parameter servers. And the parameters might come from 100 different parameter servers where the parameters are distributed evenly across those so that you get more network bandwidth into the parameter servers than if you just stored them on a single machine. And then the model replica will read a mini batch of examples from disk, will do the computation necessary to compute a gradient, and then instead of applying that gradient locally, it will go ahead and send the gradient to the parameter servers in a distributed manner. So they might be, again, spread over 10 or 100 machines. And then the parameter servers will actually be responsible for updating the parameters. And so that's one round trip through a mini batch, is you now download the parameters and send gradients, and they get applied in the centralized service. And then before the next example, you do the same thing. So now we have p prime, and change to p prime, we can get p double prime. And really, all of these machines are going to be doing this at the same time. And there's a few variations of how you can orchestrate this kind of parallelism. So in disbelief, we actually had these parameter servers were actually completely separate software subsystem. And the communication mechanism used here was not the same as the communication mechanism used, say, between different machines in the model itself, which actually caused kind of a bunch of complexity. It also meant that you only could select from a handful of parameter update rules. You didn't have the full generality of the programming language for updating parameters. You could say, OK, I want to apply a standard learning rate update or a learning rate with momentum or a few things like that, but not a much more general thing. And so that ended up being much more complicated. And so we dispensed with that separate system in TensorFlow. And so because the send and receive nodes sort of abstract away network communication, in TensorFlow, we're actually able to model the parameter server just as other devices in the computational graph. And so, for example, these things you might say that this part of the model here is a parameter server device, but it's just part of the computation graph that you're trying to perform. And it happens to have send and receive nodes to get copies of the parameters onto other machines or other devices. So the two main choices you have for data parallelism are you can do this synchronously, where you have replicas all kind of processing a mini batch. And essentially, that's equivalent to a single machine processing an n times larger batch. And for some kinds of problems, that's OK. But often, a much larger batch size means if you make your batch size 10 times as big, you don't learn 10 times as fast. The other advantage of this approach is you don't get any gradient staleness. So when you download the copy of parameters, you've synchronized everything. So everyone gets the same copy of the parameters at the beginning of the step. They compute their own individual gradients, and then you combine them somehow, either by averaging or adding the gradients from the individual machines. And so there's no issue of applying gradients to stale copies of the parameters. Another drawback, a drawback of this approach, though, is it's less fault tolerant. So if any one of the machines dies, you kind of have to do some recovery process to deal with that. Whereas in the other approach is to do this asynchronously. So if you have 10 replicas, they each kind of independently do steps as fast as they can, independent of what the other machines are doing. Yeah?
There's also the intermediate case where some machines will compute faster for some reason. That would hurt
the synchronous case more, typically, yes. So in the asynchronous case, let's say 9 machines are zippy fast, and the 10th one has some other job running on it, so it's slow. That doesn't hurt you as much in the asynchronous case, because that one just will give you, half the throughput, but everyone else kind of runs at full speed. Whereas in the synchronous case, that actually causes trouble. I'll talk a minute about some mechanisms to alleviate this. And you can also do some hybrid in between this with m groups of n synchronous replicas. So in pictorial form, what this looks like is you might have, this is the asynchronous training, you might have 3 different threads driving 3 copies of the model, all sharing the parameter device. So they all get the parameters from the same place, but then they do their own independent computation on a replica of the computation graph. And these threads kind of don't interact at all other than saying, OK, I'm done with my step. I'm going to start the next step. Whereas in a synchronous model, there's one controller for the entire process. And the computational graph conceptually is sort of 3 replicas of that computation in one graph. And you get the parameters, you do the computations on the different mini batches, and then you add the parameter gradients from the individual mini batches together to then compute what the full gradient is for the full batch, and then you update them.
Can you return to the other slide?
Yeah. So these clients could either be different threads on the same process, or they could even be separate threads in separate processes. As you scale, if you have hundreds or thousands of replicas, then you probably want these to be separate processes themselves, because otherwise this thing can become a bottleneck, and your pile of hardware here is bottlenecked because this guy can't even say start fast enough. And in terms of how the parameters get updated, every square here is an update to the parameters. And so in asynchronous replication, those just pile in whenever they finish. And in synchronous replication, they pile in this orderly, synchronized manner. We can actually introduce backup workers, where in this case, we're showing 3 workers, and we take the first 2 that finish. So this is a technique we used in MapReduce, which is a general computational framework of backup tasks, where you essentially do additional computation sometimes and take whichever one finishes first. And so here, we're actually doing slightly different computation because it's typically a different randomly selected mini batch. And then you take whichever 2 of these smaller things finish first, and then combine those to compute the gradient and drop the last one. And the real numbers are typically more like 100 replicas with 5 extra ones rather than 2 and 3. So one factor in using data parallelism in this way is because you're sending the parameters of the model over the network quite often, basically before every one of these mini batch steps, you really want the model computation time to be large relative to the time it takes to send and receive the parameters over the network. And so models that have fewer parameters but use those parameters in many different floating point operations actually tend to work better in this regime. So convolutional models are very good in this regard because you reuse the convolutional parameters for a layer at every different spatial position. And so you might reuse a given floating point number you've copied over the network as a parameter, 10,000 or 100 or 50,000 times. Recurrent models also have this property, although not quite to the same extent, because you're typically unrolling through time, and you might unroll 20 or 100 steps. And so you get to reuse that floating point value that you've brought in over the network 20 or 100 times in that case. So data parallelism actually is a really important tool that we use pretty heavily. So for example, training one of our ranking models for search, we use 500 replicas. We use 50 GPUs to train some of our large image models for ImageNet, and typically get maybe a 40x speed up. We have a system called Smart Reply that uses 16 replicas, each with many different GPUs. So this is pretty important for getting the turnaround time low. And just to illustrate this in pictorial form, so what we have here is this is an inception model trained on ImageNet. And what you see is the x-axis is hours of training time, and the y-axis is accuracy. And so if you look at the difference between 1 GPU versus 50, we're getting a 30.5x speed up with 50 GPU cards. It'd be better if it was 50, but it's not. But it's clearly much better. The other thing we've been investigating a bit is going back to using more synchronous training techniques, just because the noise and the gradients that you get in the asynchronous regime tends to mean that you can't quite get to the highest level of accuracy because of that noise. So this blue line here is an asynchronous training with 100 replicas. Be aware that the y-axis is quite compressed, so it's 0.77 to 0.795. So these are fairly subtle differences, but still, if you care about that last little bit of accuracy, you can see that the asynchronous training kind of tops out at like 0.785 here, and you get another 0.5% or almost a whole percent of accuracy in the synchronous training case, because the noise and the gradients actually just means you bounce around a lot rather than actually descending to the bottom of the valley like you want to.
Even if you decrease the learning rate?
Even if you decrease the learning rate, and yeah, that's our experience. Or you have to decrease it so much that then the training time becomes sort of untenable. And so if you look at this, if you compare, several different comparisons are interesting here. So one is asynchronous versus synchronous training. And you see you get to the same level of accuracy for synchronous training in 40 hours instead of 52 with basically the same amount of hardware. Another good comparison is this synchronous of 100, but we also have 5 extra workers. So we're now using 105 replicas instead of 100. So it's 5% more hardware. But that got you a pretty big win, because now instead of 40 hours, it's 30 hours versus 52 hours. And if we compare just the synchronous 100 versus the synchronous 100 with 5 extra workers, you throw 5% more hardware at the problem, but you get a 25% reduction in training time. So, and these are all relatively easy to express as TensorFlow graphs in various ways. And there's an archive paper about these experiments, essentially. Any questions about any of that? Yeah?
Can you talk more about why just throwing 5 extra workers leads to such a huge number?
Yeah, so in part, it's because these machines are in Google's data centers, and there may be other tasks running on the machines sometimes, or there may be network traffic on the network that is interfering with some of the machines more than others. And so what that means is you have a fair amount of variability in how long it takes each machine to complete a step. So the median might be say 1 second, but the 99th percentile might be 1.4 seconds. And if you're waiting for the last guy, the 99th percentile is what you actually care about, because you have 100 guys and you have to wait for the last one. And so basically by doing 105 and taking the first 100, you're able to bring it in so that what you care about now is the 95th percentile latency rather than the 99th. And it just tends to be that in these large data centers, there's just a lot of stuff going on. There's like background processes waking up on the machines every so often to compress logs, and there's extra traffic on the network, and the machines are overheating, so some of them are like slightly underclocked because of that. And this just makes it more robust to that sort of thing. And you can't sort of eliminate all those sources of variance very easily. So it's best to just build the system to be more tolerant of them. Yeah? This is a dense model. So this is an ImageNet model with a convolutional kind of set of parameters. So not super many parameters, but a lot of computation per step.
So we see the same like as big differences than in sparse one?
In terms of accuracy, or?
Yeah.
Probably not as much, because the thing that's killing you here is the conflicting updates for the asynchronous updates, because the parameters move in the meantime. And in sparse models, that's less likely to be the case, because the interference pattern looks more like that rather than like that. Yeah?
So I guess the reason we need these backup workers is mostly because slowdowns due to the machine. But what about slowdowns due to the data itself? Let's say some data is just harder to process. You make sure that you will eventually process these batches, or you don't leave that on the floor and you will.
Yeah, I mean, the assumption here is that most trips through the model are roughly the same. So that's true for image models, at least these dense image models. If you start to have branching in the models, then you probably would need to add some extra mechanism to keep track of the probability of sampling a particular example and make sure you don't drop examples in an unbiased manner, or in a biased manner. Yeah.
So the 30.5x you had in the previous slide, was it with synchronous plus extra or asynchronous, or what method?
This was synchronous, I believe. Yeah. Yeah.
I don't know if you're going to talk about model parallelism or not, but I just want to know how do you feel about the whole data parallelism story? Because in disbelief, as far as I know, the only possible model was the model replication over many devices. But that has been changed in TensorFlow. In TensorFlow, it's TensorFlow is capable of fine tuning of how data is being transferred between everything. So is that because you think that data parallelism is an end? Because based on these graphs, it seems that it can scale only to 100 machines, not more than that. Just how do you think about it?
Right. So actually, disbelief also supported model parallelism. So if you think about this in either TensorFlow or disbelief, each one of these yellow rectangles could be a separate machine that has got model parallelism involved in the model itself. In fact, we regularly train, for example, language models or sequence-to-sequence models where each one of these might use 16 GPU cards because it's a very deep model with 16 layers, and you could get pipelining, as I'll show you later, in terms of model parallelism. But then you also have data parallelism where you have multiple replicas of those 16 GPU setups. So it's not like you have to pick one or the other. Often both of them are good to do, depending on your tolerance for what you want. Where was I? Other questions? Okay, so we originally designed TensorFlow to kind of generalize the kinds of computations we wanted to do in terms of the deep learning research our group was doing. But it's actually pretty flexible. So I think what we'll see over time is that a lot of other kinds of computations can be expressed in TensorFlow, and the kinds of optimizations we're starting to do and we'll do more of will make lots of different kinds of computations expressed as TensorFlow graphs run efficiently on sort of very heterogeneous hardware. I mean, it's a very nice model that you can express this abstract graph and then say, I would like to use 16 GPUs, please, and have the system automatically place the computation or have hints about where the computation should be placed. So as I said, it runs on the variety of different platforms, which is important for some kinds of applications. And in particular, we're starting to see people building custom machine learning hardware that make certain kinds of operations that you see in deep models much more efficient than on CPUs or GPUs. There's a company called Movidius that has built this kind of very low power custom ASIC that doesn't have a huge number of raw flops, but actually does a fair number of flops per watt. And they have a little evaluation USB stick, so you can get one of these and plug it into your laptop and have an accelerator for different kinds of models. I think the typical application they're imagining is something like a drone where you actually want onboard image models to run efficiently and not drain your battery too much. And Google has actually built a custom ASIC that I'll talk about in a minute for mostly for accelerating inference in data centers. And I'll talk about that in a moment. But I think a really likely trend is that there's going to be much more heterogeneous hardware in data centers and also in mobile devices, because essentially general purpose CPU performance scaling has stopped following Moore's law. Basically, you can't make general purpose CPUs that give you the performance scaling we were getting, say, a decade ago anymore. And so specialization of hardware for different kinds of workloads will be much more important. And because deep learning has this handful of primitives that are really important, things like matrix multiplies or element-wise vector operations, there'll be a really big opportunity to specialize hardware. And they're also very tolerant of reduced precision and noise. And that is a pretty different design point than, always correct logic in your 32-bit multiplier that you might have in a general purpose CPU. So I think that'll mean that people tend to look at what kinds of things can we do that are a bit more specialized, especially because unlike other kinds of specialized hardware that might do encryption well or might do compression well, if you believe that deep learning is going to be in pretty much everything, then you can build specialized hardware, but it's not really so specialized, right? It like actually does everything you want, which is kind of nice. So Google's take on customized hardware is this custom machine learning ASIC that our chip design team built. And it's been in production use for almost a year and a half now. It's used on every search query. It was used for the AlphaGo match in March against Lee Sedol in Korea that DeepMind arranged. So you can see the rack of machines that was used for the AlphaGo match with a little commemorative Go board on the side. And essentially, it gives us an order of magnitude better peak performance, but also performance per watt over things like GPUs and CPUs. So we think that's pretty important. The other thing it gives you is because it has higher peak operations, it means you can employ fairly computationally expensive models at lower latency. And for a lot of interactive kinds of applications, you really care pretty deeply about responding quickly to the user.
So you said it's pretty general, it's doing tensor operations, but you also said it was only used for inference. What's missing for doing training?
It just turns out that inference requires a bit less precision than training generally. And so if you want to build something specialized for inference, then you might want to build something with even lower precision than really can be accommodated for training.
But in the TPU, what kind of precision do you have?
We mostly are doing 8-bit operations.
You can train with 8 bits.
You can. It's harder. But definitely 32-bit floating points are overkill for training. So there's
16-bit for the weights and 8 bits for activations is plenty.
yeah, maybe with some scaling and so on. Yeah, question up there? So the first part was, is it expensive? Priceless. We are not currently selling them, so right. Well, I mean, we look at performance per dollar in terms of the solutions that we have available, and we think it's better than other solutions out there. So you can infer from that what you like, I guess. We don't currently have any plans to announce to make them available, but it might make sense down the road to maybe not sell them, but to sell the ability to run computations on them. Okay. I think machine learning hardware is going to be interesting because I think hardware designers are just starting to really look at what you can do given the kind of relaxed constraints of lower precision and maybe noise in terms of what that might mean for designing hardware rather than having to always get the right answer, say. So I'm excited about that. So TensorFlow is also extensible. So the core system defines a bunch of standard operations, which are kind of these abstract things like matrix multiply or element-wise vector add. And then also kernels, which are implementations of operations for particular devices. So we have this kind of two-level model of the abstract operations and then different implementations of those that can be mapped onto different devices. And not every operation will have an implementation for every device. So if you have something that only runs on CPU, you just wouldn't have a GPU kernel for that, and the system would know well, my available choices for running this have to be on a CPU because that's the only kernel that I have for that. And it's relatively easy to define new operators or kernels if you want to do something that's not covered by the standard thing. But that's relatively rare for our machine learning researchers generally to want to do that. OK. So let me take a bit of a lower level tour now through what's actually happening under the covers when you're expressing different TensorFlow things. I was going to put together some slides, and then I discovered this person, Kevin Robinson at MIT, had put together a great set of slides that were covering mostly what I wanted. So I asked him if I could use his slides, and he said yes. So the slides with this background are thanks to Kevin. OK, so some of this I kind of already talked about, but basically you have this computational graph. And each one of these things is an op. And as I alluded to, it has kernels. So you express these ops. This is similar to the example I showed you earlier, but all in one slide. And we're going to have this little running example to go through these things. We're going to have a weight matrix, some input, a bias term that gets added together in a ReLU unit, and some cost function. So now if we look here at the matrix multiply, what that really means is we're going to take the tensor flowing out of W and the tensor flowing out of X, apply the matrix multiply operation, and produce an output that will flow into some other part of the graph. And so in Python, you would write this, tf.matmul w, x. We actually automatically generate Python wrappers for the lower level representations of these things. Because in C++, we have a matrix multiply operation that's got a variety of different options, like is A transposed already, or is B transposed already? What is the type of the underlying elements? And so this call here will generate a call to here saying basically it's not transposed. And so this is Python code. This is code the user wrote. This is code that's automatically generated by our wrappers generators from the operations that are defined in C++, in the C++ code done here. So now we're going to zoom along, and this is now where we actually are going to execute the graph multiple times. And so we built the graph. This shows you the graph, and we have a visualizer that allows you to see what the graph that gets constructed by your TensorFlow program looks like in this visualizer front end called TensorBoard. And so you can see here we have an assignment to variable W, and we have a read of this variable. And then the optimizer functions extend the graph. So this is where the automatic symbolic differentiation happens. So in particular, if I say minimize the cross-entropy loss here, then it's going to automatically compute derivatives of the various variables in my parameters in my model with respect to this cross-entropy loss. And will do the right extension of the graph. I mean, it's sort of drawn in this slightly weird way, but really you can think of it as just more graph. And this is very much how Theano operates as well. And then one of the ways that the graph, the actual computation, gets communicated around is through a serialization mechanism called protocol buffers. So that's a way of expressing what the graph is in a way that can be sent across machine boundaries pretty easily. And so here we say, please give me the graph as graphdef, which is a protocol buffer. And so here's a node with a matrix multiply operation where we're having W and X, and they're not transposed. And then there's an add operation and a ReLU. And so that's kind of the representation of those three graph nodes in the graph. There's that one, there's that one, there's that one. OK, let's see, where are we in terms of time? Let's keep going a little bit, right? We break at 4? OK. Or 1 for me. OK, so now let's look at how we actually get these graphs distributed across multiple devices. So in a distributed setting, there are many different processes involved. There's a client process, And then there's typically a master process that is responsible for kind of coordinating all the different operations that are going to be performed and orchestrating the graph execution. And then there may be multiple worker processes involved in your model, which may have multiple devices. So when you create a new session that says, please give me a way to talk to this master coordinating process. And so over an RPC layer like gRPC, that has, so here we say I'm going to create a session. And then it's going to send an RPC to the master service with the saying, please create this session to execute this graph. And that's where the graph that you've constructed in your client program actually gets converted into the serialized form and sent over to the master, where, so now we have the graph on the master. And later you would say, please run this graph, and I would like to feed in for the value of x in the graph, this particular input value. And so that gets sent over as well and gets converted into a run step call. It says, please run the graph given this data that's being fed in for x. And you can also say, I'd like to fetch the value of the cost of the model or whatever. And so now that coordinator is going to talk to the various workers involved in the process. And it's going to say, please run this graph for the part that you have. And these things might have receive and send tensor operation, receive tensor calls that communicate tensors amongst these different workers as necessary to execute the entire graph. So one of the things you can do in TensorFlow is you can say, here's my general graph, but actually on this run call, I only want to execute and fetch node F. And by the way, I'm going to feed in this value for node C. And so conceptually that gets converted into this, and then we can then determine, because we only want to fetch node F, we can determine the transitive dependencies that we need to execute in order to compute the output of node F. And when we do that, that means we don't need to execute these other nodes in the graph in this particular case. So this is a pretty general technique in TensorFlow where you express perhaps many different kinds of things you want to do in the graph in a single graph, and then depending on what operation you want to do, you execute just a piece of that graph. So we often, for example, have some part of the graph sitting off on the side that has checkpointing operations for the parameters in the model. And normally we don't execute those, but then every 10 minutes or something, we'll execute this other part of the graph that is going to checkpoint the state of the model onto disk or restore it, for example. But most of the time we might not execute those. And that's a pretty general technique for having a single static graph that can be a little bit dynamic. So one of the things that we need to do once we get this graph in the master process is figure out where we're going to place the different bits of computation. And we allow users to specify hints about that. So you can say, I would like this particular set of variables to be placed on this job, task 0. This is how you might, for example, use a parameter server and distribute a few of the parameters in your model across different parameter servers. And then I would like this bits of computation to be done on task 7. This is sort of unideal. Ideally, we would just take the graph and figure out where we want to place things. But that's slightly more aspirational than actually works in practice today. So we allow people to specify hints. You don't have to specify hints for everything. If you specify a few hints, that'll kind of anchor bits of the graph, and then the rest of the stuff will generally happen correctly. And we have plans to work on this more seriously to actually do a good job of actually measuring where we should be placing things. This is actually an interesting machine learning problem in terms of, because it's actually very amenable to reinforcement learning, where you want to place nodes here, and then you can get a measurement of how long the graph takes to execute, and then say, oh, well, that was a bad idea. I should have placed it over here. And then the trick is you want to be able to generalize from experience with one graph to similar kinds of graphs. So we think that that might be an interesting problem to work on. All right. So here is the placement. We might decide to place, for example, these nodes on this device and these nodes on this device. Or these could be devices in the same process, but are different GPU cards, for example. So you see the difference there? This is actually a separate process, maybe on a different machine. Or they might be different devices, but on the same machine. 2 different GPU cards. And so one of the first things that happens is we partition this graph into subgraphs after we've made placement decisions, and we insert the send and receive nodes. And then we have this thing called a rendezvous. That's how the send and receive nodes kind of coordinate their activity together. Right. And so let's see what happens when we do run graph. So we're going to execute this graph. There's a kernel. So if the operation here, A, is for a matrix multiply, we're going to find the corresponding kernel, and we're going to execute it. If it's a conv2D operation, then there's a different kernel that's defined for that, or an op for that. And there's different kernels specified, so this is the C++ code that gets registered. Mostly, if you're using TensorFlow from the Python level, you don't have to care about any of this. You just care that the right operations for your model are there. And so, for example, here's the matrix multiply operation. And every operation, every kernel has a compute method, which is what gets invoked on every step. And that allows you to access your input tensors and then perform operations on them. So in particular, this will launch a matrix multiply operation on A and B and do the right thing. This is a different way of doing it. Not so exciting. This allows you to get a stream context for GPU devices. So we've abstracted away the cuBLAS interface a bit so that we can, for example, use a stream execution stream for GPU cards and have a different implementation of it for, say, TPU cards. And there we go. I think I'm going to skip most of the rest of this because it's not super interesting. Right, so one of the benefits of the session interface is that you can essentially specify this graph and then call run many times. And that's typically what users do, is they set up their model and then you run thousands or tens of thousands of steps through your model. And so that provides a big opportunity to do significant optimization work. And we do some of that today, but we intend to do a lot more in terms of generating really good code for the particular sizes of tensors that are flowing around in the model, which are not necessarily known at compile time in our case. OK, so why don't we take a break now? Does that seem like a plan? And we'll come back in half an hour. Is that right? So a little bit before. Oh, yeah. Are there questions before we take the break?